Hey everyone, we're back. Heat distribution. So we've been talking about. We just went through heat distribution by way of wind or the atmosphere. In this case, we're going to be talking about the water. And actually, it turns out wind is really easy to move. Water's harder to move, but it has a really high heat capacity. That means it takes a lot of energy to change the temperature of water. Water absorbs that energy, but that energy stays in the water. So once the energy's in there, it's really effective at keeping its temperature. Actually, one of the kind of definitions is 1 cubic centimeter of water actually takes 1 calorie of energy to heat 1 degree Celsius. Again, that's from a physics class, but really what that came from was beer brewers in the 1700s in England who needed to figure out how much energy it was going to take to boil their beer, right? So some of the kind of pioneers, James Joule, like Joule is a unit similar to a calorie. He was a famous beer brewer. So anyway, water holds on to heat really effectively. We're going to now push the water around in the similar way that we saw with the air, right? And actually, as water is being heated in some areas and cooling in other areas, it also creates currents, but it doesn't create these really simplistic currents like we saw in the atmosphere. It's much more complicated. The ocean basin is this complicated three-dimensional shape. Right? There's continents in the way. There's, mid-ocean ridges. There's seamounts. There's all kinds of stuff. And so it's a little bit more complicated. We're not going to get so much into that. But what I did want to talk about is this kind of vertical cross-section of the ocean. So we've met the idea that winds are blowing along, right? The trade winds. And what those do is the wind really creates one of the types of currents that we see in the ocean. And about the upper, roughly 10% of the ocean is moving because of friction with the atmosphere, right? As the wind is blowing across the ocean, it drags some of the water along with it. So you can see I've labeled these here surface currents. Surface currents, there are lots of them. And actually, so here you can see this is an image of the major surface currents on planet Earth. It doesn't look that different than the wind patterns, right? So generally, north of the equator, the surface currents are blowing the water to the south towards the equator, and then from the south blowing to the north, just like the winds kind of converge on the equator. Things get a little bit different when we get into the polar areas because then we start seeing really kind of significant changes in water density, which has to do with temperature. So surface currents are pretty straightforward. The ones that are a little more difficult to understand are what we call deep ocean currents. So deep ocean currents are in some ways affected by the wind, right? Because they're underneath this water that's moving. So they are related in a complicated way. But deep ocean currents, they really are vertical currents. I mean, they're horizontal as well, but they really facilitate the mixing of the ocean. And what this really has to do is changes in a couple of different things. So changes in temperature can affect the density of water. Cold water is more dense than warmer water, and also salinity. So saltier water, because we're talking about the oceans here, saltier water will sink, whereas water that's less salty will rise. So what does that all mean? Well, I'm going to erase some of this stuff and we'll just talk about deep ocean currents. So here I've drawn a hypothetical ocean. It's definitely not to scale. I wanted to just kind of, for our imagination, let's pretend that this is the equator and this is the polar areas. So the poles, whether it's north or south. So obviously this isn't going to work. But what we see with these deep ocean currents is the water here is warmer, and that warmer water will rise. And again, it will move down gradient. So that warmer water will start moving towards the polar areas. And then here in the polar areas, that water starts to cool off and it will sink. So you can get these massive kind of rising and falling currents within the ocean. And that's a significant kind of conveyor belt for heat. But it turns out this isn't the only thing, right? So here we just talked about temperature. These are types of currents that have a special name. I'm going to write it out. You'll probably be able to understand what the drivers are. So these are what we call thermohaline. Thermo, we just actually talked about that aspect, right? Warmer water rises, cooler water falls. And so in the polar areas, we generally get downwelling currents. And in the warmer areas, we generally get upwelling currents. That's tied to so many different things. You think about nutrients moving around, where animals live, what temperatures they like. Like I said, it gets, there's a lot of moving parts here. But the other thing that I wanted to talk about is, if we think about over here in the polar regions, well, it's cold, right? Everyone understands the polar regions are cold. That's what they're famous for. And so oftentimes we get big packages of sea ice. So that sea ice, as it forms from seawater, the cold of the polar regions drives ice formation, and the ice is just made out of H2O. Just water molecules, right? So just fresh water can freeze. So if you have a package of salt water and you start freezing it, what happens is the water itself is drawn into the ice, and then the salt, rock salt as it exists as a mineral, is known as halite. So haline is a reference to saltiness. So the water here is extra salty in the polar areas because the ice is drawing up the water and leaving the salt behind, almost like creating a brine. And so that's another thing that causes that downwelling current. And one of the things that we're going to explore is that the speed that this drops, or kind of the force with which these cold currents are dropping down to the bottom of the ocean, displacing other water, has to do with how cold the water is. Like, colder water is more dense until you get down to a certain temperature, then things kind of get goofy. But also saltier water. And this all really hinges on the fact that here we have seawater interacting directly with the atmosphere, right? That's fundamental. One of the things that we're going to see in a little bit is potentially there is a way that this interaction with the seawater could basically be blocked. And if that were to happen, the force that's pushing these ocean currents around is lessened, and the currents get weaker and weaker, and potentially even stop. So this is a figure of these deep ocean thermohaline currents, what some people call the global conveyor belt. And you can see, generally, if you kind of look closely and follow the arrows, we've got colder water being sourced, sinking currents being sourced generally in the polar areas, and upwelling currents being sourced kind of in the equatorial areas, right, where the warm water is rising. There's a lot of things that can change this, right? So in part, El Nino is tied to this, right? The locations of these currents and where we have upwelling heat that actually can change and cycle over time, which can kind of change the kind of climate conditions in a little, almost like a microclimate, right? We get some weird effects of El Nino and La Nina. But really, this is the most effective way that heat is pushed around Earth, right? It's brought from the equatorial areas to the polar areas, primarily by water. And actually, one of the ways that we can really highlight that is if we think about the Gulf Stream, which is probably one of the most famous ocean currents in the Atlantic Ocean. That water is warmed near near Florida, right off the coast of Florida, kind of in the Bahamas, the Bahamian region. And that water heads to the north like we would expect, and it goes into the North Atlantic, and at that point it gets cold enough that it sinks. But that water has also carried heat with it. So I don't know how many of you have ever been to London or spent time in London, but even if you have never been there, you can imagine, a sunny day in Hyde Park, or, it's famous for being foggy, but it's not famous for being very cold. But London, England, is the same latitude as Anchorage, Alaska, which has a much different climate. And the reason is the heat is being carried in this conveyor, this thermohaline deep ocean current, and that heat is being transferred from the Caribbean zone, the Bahamian area, to the British Islands, right, in Northern Europe. So that's a really good example of how heat can modify the climates of regions. Okay, well, that will do it for heat transport as a function of water. All right, catch you next time.